The organizers again. It's a fantastic conference. Discussions are great and the atmosphere is fantastic. Many thanks. Today I'd like to speak about aggregation. This is my bias. I'm fascinated by how society works, how the large scale of society works, and how by aggregating our actions, opinions, and so on, we can reach a seemingly working state. I'm not saying optimal, I'm saying working state. So I'd like to speak briefly about what I think is interesting in physics for economics. We all know that a part of neoclassical economics is inspired by 19th century physics, where you start from elements and interaction with some global optimization procedure, and also this notion of entropy. And then you can build equilibrium theories that work. And clearly, this is what was called physics envy. You start from general principles and then the idea that there is the optimization of some kind is very appealing to us. That even the smallest particle follows the least action path. That's very nice. But then, if you look at what happens in the 20th century, somehow economics didn't follow. First of all, the very nice Noether theorem. That whenever there is a symmetry, there is a concept of quantity. Energy is linked to time reversal, for example. And also the very important concept of phase transitions, that if there are interactions, strong enough interactions in a large-scale system, you cannot predict what the outcome will be. And this is where aggregation comes in. What economists call micro-founded. Well, in principle, it's a very good idea. Is that if you study how an individual makes choices, then that's very important. But then the problem is how they aggregate. They just multiply by the number of agents, and then you have the behavior of the system. And we will see later in this talk that this just comes from a reversed way of thinking that can be improved upon. Phase transitions are also fascinating because unexpected things happen. That if you add one more car in a city, then it's stuck. And also that they come in several types. One type is discontinuity, like having ice or liquid. The density is not the same, or something smooth. And this notion, I think, is absolutely crucial for economics, but has not received much call or more good reception. I remember an interview at an Oxford college for a prestigious position, and there were 50 fellows, mostly from law and economics. And the question was, what will remain of physics in economics? And I said phase transitions, scaling, and so on. And I could see 50 faces of disbelief. But I hope that this will change. Right, and then also a kind of revolution in statistical mechanics is that you can reformulate statistical mechanics as entropy maximization with constraints, and it's with constraints that will be the theme of this lecture. But then, at the end of the 20th century, something even more interesting happened. Is this non-equilibrium systems? Basically, before we are talking about equilibrium. You tweak the parameters, you let the system evolve, and it reaches a stationary state, something nice. Now, non-equilibrium systems are way more interesting, but way more perplexing as well. The simplest example is what is called extrusion process. You cannot have more than one particle at a given position. You cannot have more than one car, usually not more than one car at the same position. And therefore, the local constraint is very strong. The prototype model is called asymmetric, extrusion process, and in particular the totally asymmetric extrusion process, TASAP, whereby all the cars try to move in the same direction. Basically, you can only move to the right-hand side, and if there's a car, you can't move. That's how it works. And this concept of extrusion process has been applied to limit order books. In this limit, there is only one order per tick, and this is very useful to obtain simple results. But in this model, in fact, I have cheated. It's not the picture is not complete. What is interesting is that it is driven. There is an external source of particles, of energy, as in the Earth is a driven system. There is an external source of energy. And usually this external source of energy fluctuates. And therefore you have something external that always pushes the system out of equilibrium. And economic systems are driven systems. They can't be at equilibrium. We are born, we die, we have children, and so on. So there are natural disasters and so on. So it's completely driven systems, and this notion has yet to permeate economics, I believe. But this is, I think, one of the great development of physics recently. And in these systems, there is no notion of energy, of temperature. By being clever, you can find equivalent notion of entropies, of temperature and so on, and also of Hamiltonians, but that's only for certain systems and for certain types of dynamics. Once again, people have realized that entropy plays a more central role than physicists believed previously. But another stream of physics is very relevant to economics, is the physics of disordered systems. Disorder just means randomness, but mostly fixed randomness. What they have found is that there is then a multiplication of equilibria, if you like, but there are so many of them that the convergence to equilibrium is really, really slow, basically logarithmic, and therefore you are never at equilibrium. And once again, this is the new physics, if you like. So if I were an economist and I'd like to cherry pick some of the good bits from physics, these are the ones I would try to apply. But note that this is really ongoing research in physics, and therefore nothing is does provide a complete picture, but people are doing some nice progresses. So these are the good bits. I would keep the interactions, because clearly economic systems, or large-scale economic systems, are made of entities that interact with each other. So I would not be surprised to see herding, to see phase transitions. But lately, a fundamental insight has been that what physicists regard as physical disorder is equivalent to economics heterogeneity between agents. And therefore, there is a one-to-one correspondence, and therefore the tools designed in physics to tackle heterogeneity, disorder, can be used in economics to tackle heterogeneity. And there are basically three mathematical methods that physicists use. The simplest one is the replica trick, and its use is absolutely straightforward. You have a discrete, a set of measurements. You know that you can measure t time steps of n assets. And then you have to compute a portfolio from that. And portfolio optimization is a nonlinear operation from a given data, and this is disorder. It's drawn at random, and therefore you can use this method to compute the average optimized quantity given a set of measurements. And therefore it's very useful. We'll see when. Then there is something else. I have seen it used in mathematical finance by some mathematicians, but not so much in economics. But physicists have devised a way to solve the dynamics, the full dynamics. That means all the correlation functions, stationary state, whatever, you name it, with so-called generating functionals. So if you give any mean fields model, that means an agent-based model where there is some kind of global communication to this, it can solve the dynamics of all the agent-based models in mean fields. It's different from Pierre-Louis Lyon mean field games in the sense that there is no function that is optimized. You really start from the dynamics and you solve the dynamics. There is no optimal behavior. The agents do not optimize, they just are dynamic. And then there is what is so-called message passing algorithm or cavity method in physics, where you can you basically propagate guesses of probabilities between possible solutions, and it has been very, very successful in computer science problems. So the applications of this physical method, just a few examples. You can compute the what statisticians call high-dimensional limits, when the number of measurements and the number of elements, if you like, both go to infinity at the same time. And clearly, you can well, portfolio optimization, they have been very recent works, very nice by groups in London, Caccioli, and so on. And you can also compute bootstrap and so on. But one thing that hasn't been done by physicists is to tackle random forests, for example. There has been nice work by mathematicians on random forests, but not physicists. If you are a physicist knowing these methods, I would advise to tackle random forests. Agent-based model, the minority game stands exactly at the border between being exactly solvable and not exactly solvable, in the sense that one phase is very hard to solve despite having these methods. And it was a model so complex to solve that economists said that they need new mathematics. They felt they couldn't solve this model, and they were right, but the mathematics exists and they are to be taken from physics. In the last 20 years or so, people have been able to solve the phase transitions of complexity in optimization problems and some problems of statistical inference. So all these things have been borrowed by computer scientists, but not really by economists. But I'm sure that they will someday. So to answer the question of this conference's theme, I would say, yes, for physicists it would be natural that economics uses the tools from physics. But then there is always this objection, is that human beings are not particles with constant properties. But that is not a problem. And this is my usual answer. And it comes from computer science. If something is not compatible with something else, you just write a wrapper, right? Just try to find some way to go around this limitation. And right. Properties of human beings are not constant. So tell me how they change. Maybe the way they change has some regularity, and if they have, it's just another dynamical equation in my dynamical equations. I'm fine with that because I have methods to solve dynamical equations, right? So please tell me how things change. Fortunately, we have some results. So this is how quickly we learn a task. There are two types of fits, power law and exponential. I haven't been able to find it in the literature whether people now have settled on power law or exponential. But still, you see that people do experiments, and clearly there are some regularities. So why not putting that into models, into physics models? So we as physicists are responsible to add this. Nobody does that. So it's a bit of a shame. Now, this is how we select selectively, in the sense that if you are given a string of, a series of numbers, I know in the x-axis you have the length of the string of numbers. We tend to forget the first ones and the last ones, which is totally intuitive. We would say yes, of course. Yes, right. And by the way, all these figures are taken from a book. And it's a very interesting effort. It's a book called Empirical Software Engineering, and the author is writing it up, but he puts the new versions online on GitHub. So now it has more than 300 pages, and the author wants to account for all possible influences on software engineering. And this is where I could find all these nice reviews about human behavior. So do have a look. It's not finished, but it's a really nice book. Right, so this guy had to go to articles to extract the data by hands and to do the plot himself. But he did that. And now this is how we forget. There is this very nicely named paper called 100 Years of Forgetting. I love that. And once again, you find that people have not settled between power law, exponential, logarithmic, or even hyperbolic. So they don't really know how we forget. There are good reasons for believing that it's hyperbolic. There are good reasons to say that it's exponential. for example, for mathematical reasons, but whatever. So all this must be included into models. So this is how we learn, how we forget, how we learn selectively. Now, utility functions. What to use? Nothing is sufficient, nothing is satisfactory. But then if you ask people who study birds, they have an answer. And I very much like this work. It's called scalar utility theory. When I first saw the advertisement for the title of this talk, I thought, yes, so that will be a number. Thank you very much. But no, it's very clever. The assumption is that we store numbers as logarithm in our brain. That's it, right? But we store them with some uncertainty. So we are not that good at remembering numbers. So we say, for example, if there are 3 possibilities, for example, 2 grains of bird feed, or 4 grains, or 8 grains, we don't store these numbers as such. We store these numbers with some uncertainty, but with some uncertainty in log space. And then, assuming that we are good enough at estimating probabilities, then we can form the subjective probability in our brain, which is like this, right? And then comparing 2 outcomes is just comparing this subjective probability in our brains. So you do this, and in this case, you would have always 5 grains, and here you have a stochastic number of grains. And then to compare whether you prefer to press a lever that gives you a stochastic number of grains or a fixed number of grains, then you have to compare these distributions. And this is what they do, and to go quickly, this is a constructive way to build utility functions. It contains prospect theory, and the message is that there is one utility function for each situation. You cannot use log, power law, whatever, exponential. You have to use one utility function per situation. And of course, one question is, in what limits would a utility function be a power law, a logarithm? Nobody knows. This is an open question. So in short, I would say that physics is not enough for economics, but it does contain nice bits, juicy bits. But clearly you have to mix all that to have something nice. And I didn't speak about computer science, but they also have something to say about efficient learning, efficient ways of online learning, and so on. So you have to mix at least these 4 fields. And I didn't have the space for biology here, but clearly biologists also have their say. And this is what it will take to make economics a science, a proper science, I believe. To get it out of the ghetto of Nash equilibria, fully rational agents, and so on. Right, let's go to aggregation. For me, large economic systems are pretty successful, and they indeed can give the impression that we must be pretty clever. However, we are not the only social animals or insects and so on. And nobody will say that a bee is particularly clever. The society works well, but why does a society work, basically? So economists would say, yes, of course, because everybody has the right incentives, so everybody behaves optimally given this incentive structure, and therefore it works. Right. That's forgetting that aggregation can produce a consistent output despite an inconsistent inputs. So if everybody is voting about something in this room, we all will have diverse opinions, but maybe at the end, the average or the median is good. And then psychologists would say, yes, it works despite all the biases, despite all the non-rationality, despite all the biases, and therefore you have to sometimes to nudge a system so that it works better. And physicists would say, yes, of course, it's a self-organized, non-equilibrium dynamical system. There is nothing special about it. So you have to mix all this, right? Aggregation. You probably all have heard about the book Wisdoms of the Crowds, which gives a quite stunning example about how to aggregate opinions from people from different fields. So the USS Scorpion was lost in the 60s. Nobody knew where it was. So the US Navy asked several experts, independently, not in a committee. They would say, well, think about what you think is the best or the most likely location of this craft. And then they aggregated these opinions. It so happens that the real location of the submarine was 200 meters away from the prediction, the average prediction. That's quite a telling example. And now, if we go to examples which are not in the book of Surevsky, but are more recent, it took 2 years to find the wreckage of the famous Rio-Paris Air France flight. And why did it take 2 years? Well, this is the last known location, and the plane was going that way, north to Paris. So then people didn't know what was the cause of the crash. So they first designed a, if you like, in a Bayesian way, 95% confidence zone. They immediately looked for the craft in that zone. They didn't find anything. And then they refined their assumptions, or they added more information, and they say, well, the plane was going that way, so this would be the most likely zone. And then you can also trace back the debris where the debris were found. You trace back the currents, and you find new zones where the plane could be found. So all this takes place in a 25 kilometers radius, just to fix things. But they didn't find anything. And then a new zone was determined, this one, but they didn't find anything. And then they updated their Bayesian beliefs, if you like, and they said, well, we have searched for all these zones, so we know pretty well that it's not there. In white, it's not there. And maybe it's here, right? And indeed, they found the plane exactly at the bottom, well, just below the last known location of the plane. So it didn't explode, and then the debris flew. It just plunged vertically, which was totally unexpected. So just to tell you that even wisdom of the crowds is not as effective as you find in popular science books. And then there is the other plane that is still missing. But then if you look at the zones which have been searched, we are not talking about 25 kilometers radius. We are talking about thousands of kilometers. And then this was a state in 2015, I think, and then since then they have found debris, and you see that they traced back the currents, and then maybe it's here. But this is a huge zone, and this is why it's very hard to find this craft, even with wisdom of the crowds. So this is taken from, this idea is, and this terminology is taken from this book. So if you ask people from cognitive science what wisdom of the crowds covers, they will say, well, it's just successful aggregation of individual opinions, and thus you can have a better estimate of a given quantity. My point here is that this is not only that. This is a way to detect systemic rationality, so collective rationality. And that economic systems are a very nice illustration of wisdom of the crowds, of collective rationality, despite all of us being not rational. In mathematics, assume that there is some quantity, some scalar or whatever, vector, whose true value is x, but then each agent guesses its value. So the agent 1 guesses xii, then you average, and you find the aggregate estimates. And then the truly remarkable bits is that the expectation of this quantity is the true value. So there is no mechanism that can explain this a priori, but then when it doesn't work, in the papers, people say, no, it's not the average, it's the median. And you find that even in the paper of Galton, there is a correspondence in Nature where people say it should be the median, not the average. So if you just think about what we know about aggregation, about averages, the central limit theorem tells us that precision should increase as the inverse of the square root of n. And then extremal statistics tells you that the best expert is close according to 1 over n, so it is better than the average. And then if you do slightly more work, that means if you try to find the optimal combination, the optimal subset, so if you try to pick up the optimal subsample of experts, which is an NP-complete problem, so it takes an exponential number of steps, but then you can improve the estimates by an exponential factor as well. So it's a paper called Optimal Defect Combination. And then you find claims that wisdom of the crowd somehow can be better than the best experts. And then there are reasons to doubt of that. because it means that if you average the experts, you have 1 over square root of n, and if you take the best expert, you have 1 divided by n. So the only way it would have been non-experts, many non-experts, and then to select a random expert. So that would be how you can beat the best experts. Anyway, a nice slide with a B. Right. What does economics mainstream style tell us is that there are laws, very simple, regular laws. For example, the law of offer and demand. If you buy, for example, this is discount quantity. If you buy more of something, you will get a discount. And indeed, if you go to fish markets and you find that people who buy more quantity here of fish, they get a better price. So I have cheated here. That's not how economics works. I mean, real systems work like this. I edited these plots by hand, and I removed all the dots, all the individuals, right? So basically, economics says that each individual is like this. You multiply by n, you get the same thing. What I'm saying is that individual like this, when you take the average, you get economic rationality. Reciprocally, you don't need individual rationality to have systemic rationality. In other words, the economics idea that there is rationality is excellent, but at the system level, not at the individual level. So we can make without individual rationality, Nash equilibria, and the like, but just with proper averaging. It also means that if you want to find the real economic law, rationality, you just average the opinions of people. Here you see that we are not talking about a single number. We're not talking about a location of something. We're talking about a functional relationship. It also works for functional relationships. Yeah. In finance now, let me talk about finance. Obviously, what is optimal is that it's very hard to make money. It is doable, but it takes a significant investment of time and resources. And then in finance, you have limit order books. Limit order books is just an aggregation of individual wishes or published wishes, and then the price discovery is nothing else but an average of these opinions. And if you push that point further, you say, well, markets are efficient, the current price is the correct estimate for what we know. So that would be the simplest version of wisdom of the crowds in finance, but not so interesting. Then, if you place yourself at the level of an investment fund, you have to invest the money of other people. And what do? Well, you do your best and assume that the average fund is not that sophisticated. They do mean variance portfolio optimization or any other kind of portfolio optimization plus constraints. And that's the best they can do. They think it's best they can do, so they are not rational, they don't know what is optimal, they just know a tool and they use it. But what do we know about portfolio optimization? If you do the usual Markowitz optimization, it's wonderful because you get a weight for each asset. You will get a vector of optimal weights for each asset. But the problem is that there are too many weights. And usually people do not invest in all the assets, they select the assets. But nobody knows in how many assets they should invest. Because nobody knows our paper here, we showed that it depends, the optimal number of assets depends on the transaction cost structure. If there is a fixed cost per transaction, you get a square root. If you have a proportional transaction cost structure, you get another law and so on. And in between, you can have any kind of sublinear function for transaction cost, and you will find these kind of things. And in this paper, we found that on average, individual traders behaved as if they were optimizing a portfolio, knowing that the portfolio, the transaction value structure of a given broker scales like this. Now we are saying something else. Now we are studying how large funds behave. These are funds with more than 100 millions under management. And we take the public reports of the SEC. Every fund with more than 100 million under management that uses the US postal system, that means that invests into US equities basically, has to report its long positions every 3 months to the SEC. What we found here is a wonderful cloud of points. And see this is in log scale. So there is, for example, for given number of investment, given number of long positions, we have between, say, 10 to the 5 to 10 to the 9 portfolio value. So it's a huge number of orders of magnitude. But we find two regions. We find one region where this slope is 1/2. Is 2. And it means that indeed this square root relationship between the number of investments and how much you have in the management holds if you have a constant transaction cost, which is a fair assumption for this kind of funds. And then something happens. We don't still know why at this point. And if you would measure this exponent of the transaction cost structure, you would find something negative, which means that something else than simple portfolio optimization happens in this region. Now, quickly, a new scaling law. We studied how many funds were invested for a firm, a company with a given capitalization, and we find that it's not a integer exponent, but it's a new scaling law between number of investors and market capitalization. So here we have this challenge to explain these two plots on average. Why we have two regions here, and why we have this scaling. Now, let us first check that people aim to have equally weighted portfolios. Clearly, that's not possible. It's not always possible. First of all, because if you invest the same amount of money into a given set of securities, then, after a day, it will not be equally weighted anymore. But here we have data every 3 months. So we do not expect things to be equally weighted. Also because people do not update their portfolio every 3 months. They let it run and so on. So in blue here, we have the local average, and we see that in the region where the funds behave as simple portfolio optimizers, we have an increase of the average entropy, which corresponds roughly to the deviation you expect from the fact that price returns change the entropy. So you don't get a perfectly equally weighted portfolio just simply because of price fluctuations. And then we try to see how the funds would update their portfolio, whether they would strive to have a more equally weighted portfolio. And to cut it short, because I don't have much time left, to cut it short, this is the difference between the old portfolio and the new portfolio. So that these people try to have a more equally weighted portfolio. So that's a good check. Now, is there a limit, an obvious limit, to how much somebody invests in a given asset? If you want to build an equally weighted portfolio, you must be able to invest an equal number, an equal amount in each asset. So clearly, if you invest into Apple, that's fine. But if you invest into a very small capitalization company, you can't. Thus, if you are too big and you want to invest into too many assets, you can't. So let us first look at the region where people behave as simple portfolio optimizers. We find that they don't take into account really the capitalization of the company, so they really try to invest on average into equally weighted portfolios without any constraints. Now, if you go to the bizarre region, you find this. So one color here is one fund, and you find that each fund has clearly an upper limit to how much money he will put as a function of the capitalization. Wi alpha is how much money fund I has invested into asset alpha, and C alpha is the capitalization of that asset. So people have a very simple rule of thumb. They say, I will not invest more than X% of the capitalization of this asset. And if you talk to people who work at large funds, this is exactly what they tell you. You also see that the difference here is absolutely staggering. It's between say, a few persons to 10 to the -7. This reflects, I believe, also the capabilities of, the goodness of execution of each fund. A large fund with a good team for investing a large amount of money into a given security will tell you that they have an upper limit which is way higher than funds which do not trust really their own execution capabilities. And on the right-hand side, you have the histogram of this fraction, this maximal fraction of investments, and you see that indeed the spread is large. So here we know already something. We know that people in the right-hand side region have constraints on liquidity, and thus they have to invest into many more assets. This is why the line doesn't continue like this. They have to invest into many more assets for the same amount of money because of liquidity constraints, and you find that in the data. This is how they, briefly also, how they select. I mean, then if you do this, it's very easy to make a simple model that reproduces these plots. But then there is also the mystery of how a fund selects a given asset. So if you select n assets, and much smaller than the total number of assets, do you have a preference for large capitalization assets? And thus we measured this for different quantiles of the number of assets. And we found that indeed people do not behave in the same way depending on the region where they are. And thus one also has to take into account this preference for large capitalization depending on the region. If you use these two ingredients, then you can reproduce these two figures. The yellow orange line is the local average, and the dotted green line is the model. So you see that you can reproduce very well the average behavior with some deviations for large capitalization. Yeah. Right. What is interesting here is that these hedge funds did not know that the optimal number was a square root, well, dependent as a square root of the number of their fund under management. So, but still, if you take the average over the population, you find again the rational benchmark. And this is a very good example of this wisdom of the crowds, which allow you to find collective rationality, even if the agents do not know the rational benchmark, either because it's impossible to find analytically, or because they just don't read the good papers. I'm joking. What we also find is that the dispersion in this crowd of points is absolutely huge. And why is that? It's maybe because every fund has its own constraints. Do not invest into more than X asset. Do not invest more than X% into this sector, into each asset, whatever. They have all kinds of constraints, legal constraints, and so on. And thus, what is missing, I think, is deriving a generic way of having a rational benchmark in the presence of very heterogeneous constraints. That we don't know. So my final conclusion is that, well, if you like it to be more like a physical science, please help yourself. Many physicists will be very happy to collaborate with you. And that's it. And also, that this simple idea of wisdom of the crowds, I think, is much more powerful than just simply estimating the weight of meat in a cow. I think it can really extract economics from this Nash equilibria, rational agents, and so on, and not losing the global rationality, the fact that economic systems work pretty well. But it's accepting that even as researchers, we are much dumber than we think. Thank you very much.
Yeah. Hello. I wanted to ask you something about wisdom of the crowd. So, when you said that wisdom of the crowds gives a good estimate of the true value, isn't it also kind of a tautology? Because most of the time in economics, the true value will depend on the crowds and what the median value the crowds give. In a way. Like, for example, price setting itself is done by what majority of the people think the price should be. So isn't wisdom of the crowds essentially the true value? So,
well, to the best of what people know, at least for prices in finance, nobody knows really what determines prices, instantaneous prices, except that there is a lot of noise. So I'm not talking about say only prices, but really average decisions and so on. And it is maybe tautological, but I think that from a modeling point of view, one needs to free oneself from this each agent is rational, is the same, blah, 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 and replace that with something much simpler, even cellular automaton with different abilities, whatever. And this is how I think many topics will be able to work together and merge.
So, very mainly like looking at the whole idea of like wisdom of crowds. Let's say there's a true distribution, and everyone in their mind have their own idea of what the distribution looks like. Then you can expect that if it's a multidimensional distribution, where like if you have people are like with respect to the original distribution, if they're skewed in different direction, and a good number of individuals are like, imagine like if let's say the skewness which each of the distribution, each individual has with respect to the real distribution is a representative of their biases. Then you can say that if the people have biases of all sorts, then I can see how the convolution would actually result in something close to the actual one. But how often is this true? That people might be, if most of the people hold very similar biases, then you're going further away from the real distribution in that case. So that's a total possibility, isn't it?
Well, in a one-shot view, absolutely, yes. But usually the dynamics is repeated, and therefore you might expect that people revise their expectations or their opinions, and this skewness disappears. Here, for example, we computed the distribution around the average, and it's not skewed, for example.
Same point, like what they're revising, I agree. That's under the assumption that there's a true distribution. If people are revising with respect to what the average is, then if you start skewed, even the ones who are probably not skewed, who are probably closer to the real distribution, might actually go further away.
Mm-hmm.
So,
absolutely, and then it becomes a dynamical problem, and so on. And I think it becomes a much more interesting problem because you have to make it self-consistent, and so on, and to understand how the dynamics might be able to eliminate that skew, for example, and so on. And indeed, you're totally right, and it's very interesting. That's my point. I'm not saying that it works all the time and so on. I'm just saying that if you assume that what you see is rational because we are all rational, it may contain that skew. But if you start from a population with a skew, then you are in much better shape to understand what's happening.
Okay, so I have one question. Yes, human being are psychological being, so there is a rationality there. So maybe there is something called psychoeconomics also, where you can just take the psychology along with the collectivity.
Sorry, could you please?
Some psychological economy where
yes.
the psychology of the collectivity
Mm-hmm.
goes along, not the just a liar kind of phenomena where one or two people are just doing the different thing. They are manipulating or something like that, but there is a collective wisdom going along.
Yeah, yes, absolutely. Yes, absolutely. That's something that must be investigated. Yes, yeah, you're right. Yeah.
Okay, thanks. This big. Okay, there is one.
I'm still there. So, two dimensions. One, this is very interesting, and in economics, actually, there is a huge stream of literature which analyzes the wisdom of crowd, and which partly reflects to a basic assumption that how we are making the errors, you have to make some kind of distribution, and you apply deep group learning model, for example, to come up to the specific value, right? And so that was borrowed from computer science. And also there is Bayesian learning and so on. So one thing is that the example that he gave is, I think, wrong. So prices are not set with respect to what other people are thinking, but I think there is a deeper truth there. Many variables in economics which actually follow something called this Keynesian beauty contest. That it's not so much about what I think is good, but what the median of the rest of the population would predict to be the most beautiful one or the good one. So which is where, and I sort of see how you'll object to it, saying that again relates to another idea of consistency. Where it breaks down is one big problem, which is why in economics it's actually extremely difficult to make a prediction, because you can have in a system multiple equilibrium. So think about 10 countries lending to one emerging country, and that happens a lot to many of the poorer countries. All the deep pocket investors would invest in it, and in the good time, whenever the when the country is doing good, everything is going fine, they remain invested. But if there is a slightest review mode which has nothing to do with the fundamentals, everyone thinks that everyone else will get out. So everyone pulls out. So a priori, both of the equilibria are perfectly rational because both of them are self-consistent. So
Yes.
basically what I'm trying to say is that in a large game you can have multiple Nash equilibria. And it's often very difficult to a priori figure out which equilibria is going to materialize. Which is where wisdom of crowd, I think the fundamental additional assumption one has to also make that there is a fundamental somewhere there. Because otherwise, if the economic fundamentals themselves depend on what people are thinking to be fundamentals, then you can have multiple schemes, all of which are a priori consistent. So
Yes. So maybe I can make my point clearer. What I mean to say is that what is interesting is the dynamics of imperfection, and it's not the equilibria per se, because in driven systems you never reach them basically. You can reach, I mean, because there is external source or sometimes large fluctuations. And of course it makes sense to try to understand where the dynamics might converge, but on the way there will be many perturbations, and even in financial markets people try to price things, and all the biases are here. What I didn't say here is that there is this heterogeneity, but this is a dynamical, this is just a snapshot. We have 60 snapshots, and it's known that that level of noise, if you have a system with positive feedback, has a huge influence on the dynamics itself and on the convergence of imperfection. And indeed, you're right. I know that economists know that people are not rational. They know that you make the sum and then you get something better. But then it's about how you deal with that by assuming that, okay, let's have a simple life because and assume that everybody is rational. Or also, let's assume that our students are really stupid and just teach that. Or what I mean to say is that there is a missing link between what economists know, and they know exactly what they should do, but then there is the missing method that then will make them able to reach their goals. This is what I mean. Many economists are fully aware of that, and even the proponents of individual rationality know that it's an approximation. But everybody is doing his best depending on his tools. That's really my point.
Okay. Next speaker, once again.